All right, welcome everybody to the IRIS webinar for this week. This is a webinar sponsored by the IRIS's Transportable Array Working Group, which is part of our USArray standing committee. I'm Andy Frassetto. I'm broadcasting from the IRIS headquarters office in Washington, D.C., and our speaker is Chris Walker, who is a research scientist at the University of California, San Diego. And UCSD has been a really vital part of the EarthScope program. They operate the array network facility for IRIS's U.S. array stations, and they also operate a large portion of the global seismic network. So it's great to have a speaker coming to us from UCSD. So just before we get started, I wanted to make sure that everybody knew how these things operate. Chris is broadcasting from his computer in San Diego, and the way we'll handle it is he'll give his talk sort of like a standard colloquium. And if you have questions, comments, concerns during the webinar, enter them into your questions panel. People have been using that already to let us know that the audio is okay. But what we'll do is, as those are coming in, I'll keep track of those, and then afterwards, like we would do in a normal academic department colloquium, I'll rattle off those questions to Chris, and then he can answer them directly. And then throughout the whole process, we'll be recording this. So if you want to access the webinar later, if there was something that you thought you missed, it'll be uploaded to YouTube and available through Iris's webinar page. And just so you have the URL for that, that's www.iris.edu/HQ/webinar. And that has information about the when we're going to have the next one scheduled and access to all the previously archived ones. So, okay. So without further ado, let me turn it over to our speaker for today, Chris Walker. Chris has a background in active and passive source seismology originally, and when he went to UCSD, it was to work on seismology and infrasound, and I guess his talk today will be mainly on infrasound. So, Chris, thanks very much. I'll hand it off to you.
Thanks, Andy. Well, depending on where you are, good morning, good afternoon, or good evening. This talk has contributions from several collaborators. I give thanks to several others. I won't go over this list explicitly, but I wanted to include it nonetheless. Today I'm going to talk first about what infrasound is, how we work with infrasound, and why we study it. Then I'm going to briefly discuss several past and current USArray studies, including a study of the 2008 Northeast Oregon bolide, the detection and location of repeating infrasonic sources in the western U.S., a small study of modeling infrasound generated by a repeating source in Idaho, in which standard atmospheric velocity models are shown to have accurate stratospheric wind directions, a larger study of modeling infrasound generated by a repeating source in Utah, in which the effects of gravity waves are shown to be critically important in propagation modeling, the detection of repeating sources in the eastern U.S. and improvements being made in the associated source location method. Finally, I'll discuss some long period studies involving tornadoes and gravity waves before I conclude. So, what is infrasound? I understand the audience is broad today, so some of these are going to be pretty basic slides. Infrasound is created by the compression of air. It is acoustic energy below the 20 Hz frequency threshold of human hearing. This figure shows 4 different types of Earth energy transferring phenomena. The x-axis is the period of the signal as measured at a stationary point. The y-axis shows the physical size of the wavefronts. The propagation velocities are determined by the location of these energy types in this graph. Turbulence, which creates wind noise, is advected in the wind, and it consequently has an average velocity of 1 to 10 meters per second. Atmospheric gravity waves travel at 5 to 20 meters per second. Infrasound travels at the speed of sound in a windless atmosphere about 330 meters per second. Radio waves are, of course, seismic waves and travel consequently much faster at around 3,000 meters per second. Infrasound travels in atmospheric ducts or waveguides, sometimes to great distances of many thousands of kilometers with little attenuation. All of these waveguides are bounded at the bottom by the Earth's surface, an efficient reflecting boundary. There are three primary waveguides: ground to troposphere, ground to stratosphere, and ground to thermosphere. Waveguides are defined by the temperature and wind structure. Because the atmosphere is an advecting medium, the speed of infrasonic propagation is governed by the sum of the static sound speed, proportional to temperature, and the dot product of propagation direction with the wind velocity. This is called the effective sound speed. The altitude at the top of the waveguides is generally determined by the altitude at which the effective sound speed is the same as that at the source height. Horizontal winds in the troposphere and the stratosphere often permit infrasound generated from surface sources to travel downwind in the direction of the wind in those tropospheric and stratospheric wind jets. However, the elevated temperatures in the thermosphere make the thermospheric duct more isotropic in the sense that infrasound trapped within it travels outwards in all directions. There are many different natural sources of infrasound: hurricanes, tornadoes, meteors, opposing ocean waves at the same period, volcanoes, and auroras all generate respectable levels of infrasound. There are also many anthropogenic sources, including explosions, rockets, jets, wind farms, and industrial activities. Regardless of the type of source, they are all useful for studies of the physics of infrasonic propagation and the medium through which it propagates. Now I should focus to how we deal with and study infrasound. First, we need to measure infrasound, of course. Because infrasound has a very short coherence distance on the order of 1 to 2 kilometers, we traditionally measure infrasound with arrays of 4 to 10 low-frequency microphones or microbarometers over an aperture of 1 to 3 kilometers. Using standard array processing methods, one can separate infrasound from other types of pressure anomalies and determine the direction of arrival of the signals of interest. Because turbulence generated by the wind makes measurement of infrasound difficult, one attaches mechanical wind filters to the microbarometers. The most popular filter is called a rosette, shown here. A rosette is a series of interconnected pipes with inlets along its periphery. Spatially coherent infrasound enters the inlets and travels to a central summing manifold, where the signals coherently sum and are recorded by the microbarometer. Spatially incoherent wind noise enters the inlets as well, but destructively interferes at the microbarometer, leading to a signal-to-noise ratio gain. A typical, not all, but a typical research problem involves the detection of infrasound on several arrays, estimating the source position from a cross-bearing approach, modeling propagation from that source to the arrays, and comparing the final predictions with the observations to identify the ray paths and predict the group velocities. For many years, the study of infrasound was made difficult by the lack of knowledge of the constantly varying temperature and wind structure. A game changer occurred in 2003 with the development of the ground-to-space, or G2S, atmospheric modeling system. The system was pioneered by Doug Draub at the Naval Research Lab. Essentially, an empirical model of the winds and temperature structure above 50 kilometers is blended together with numerical weather prediction models below. Due to the inherent limitations of the input models, the structures that result generally vary over wavelengths greater than 100 kilometers in the X and Y and 1 kilometer in the vertical. However, relatively new enhanced G2S models now exist that use higher resolution input models in the troposphere. Lastly, the G2S system can be run in nowcast or hindcast mode, which allows for its use in near real-time applications. Ray tracing is typically used to rapidly model infrasonic travel times, relative amplitudes, and horizontal deflections due to the wind. However, its use is generally limited to high frequencies above about 1 Hz. This example shows a source on the Earth's surface. Rays are launched in all directions away from that source. Color is the effective sound speed with the horizontal wind speed. Color is the effective sound speed, in this case defined as the sum of the static sound speed with the horizontal wind speed in a ray reference frame. The stratospheric wind is blowing towards the left, so the effective sound speed is greater in the stratosphere for downwind propagation than it is for upwind propagation. This is leading to a downward stratospheric waveguide. The stratospheric rays are black and thermospheric rays are gray. One can see that there are shadow zones and zones of convergence of the rays for both the stratospheric and thermospheric returns. We'll see these shadow zones in map view during a later slide. A phase nomenclature system was developed by Michael Hedlund that is modeled after that used in global seismology. This system works very well, can be adapted to explain new arrivals easily. The first letter indicates the initial motion, either up or down. Since the source is on the surface, they are all U. The second letter indicates the height of the turning point in the atmosphere. T thermospheric, S stratospheric, or W tropospheric. The subscript indicates the number of turns made at the top of the waveguide. UT, 1 turn. UT2, 2 turns. When diffraction and scattering effects are important, or for relatively large sources, full wave field modeling methods are required to model the propagation. There are several methods that exist, including parabolic wave equation methods, finite difference time domain methods, pseudospectral techniques, and modal expansion techniques. So, why is infrasound studied? A practical application, of course, is the monitoring of atmospheric nuclear tests. For this purpose, the Preparatory Commission of the CTBTO installed 45 global infrasonic arrays. The design goal was to locate 1 kiloton or larger sources with at least 2 arrays using a cross-bearing approach. Simulations and experiments suggest the average array separation of 2,200 kilometers is sufficient for this task. Infrasound is also inherently an interesting energy field that touches or connects many disciplines. For example, these authors are studying the effects of infrasound generated by a space shuttle launch on the dynamics of charged particles in the thermosphere. By processing travel time delays between a GPS satellite above and ground stations below, they calculate time series that are sensitive to the total electron content in the thermosphere. Infrasound from the shuttle launch perturbs the ions in the thermosphere, generating a signal that was registered by many GPS stations in southern Florida. Using a magnetohydrodynamic modeling code, the authors reproduced the observed signal at many of the stations. Another interesting subject is the generation of infrasound from earthquakes. The Earth's surface, when excited by seismic surface waves, radiates infrasound due to the vertical shaking of the flat ground and horizontal shaking of regions of significant vertical relief. This is a map of the Tohoku earthquake epicenter and the different infrasonic stations that registered infrasound from ground shaking in the epicentral region. The colors are not important for this talk. The next slide will show the result of back-projecting infrasound recorded at USArray IS-44 to the source region. For this back projection, we had to apply ray trace modeling to predict the group velocity of the observations that were observed at IS-44. The Japanese K-net comprises about 700 surface accelerometers. These accelerometers recorded the spatiotemporal distribution of surface shaking. We now map the peak intensity of acceleration in the east-west, north-south, and up-down directions. The absolute amplitudes and units are not important. The back-projected infrasound from IS-44 illuminates the complex geometry of the land areas that experience significant levels of shaking. There are two different back projection methods that were used. The fine details are different, but the general features are the same. The most intense shaking occurred near Sundai, which is adjacent to an area of high-frequency seismic radiation imaged by P-wave back projection studies. Volcanic eruptions are also known radiators of infrasound. This is well demonstrated by a study by Matosa et al. In 2007. They deployed a microbarometer array about 13 kilometers from Mount St. Helens. They were fortunate enough to have recorded an eruption with the array and a co-located seismometer. The pressure time series and associated spectrogram shows a significant immersive wave train about 5 minutes long with frequency content up to about 10 hertz. This is the eruption signal. The co-located seismometer did not record a significant signal from the eruption. This is perhaps not unexpected since eruptions transmit intense levels of elastic energy into the atmosphere. Infrasound clearly has a useful role to play in volcanic eruption monitoring. The interaction of opposing ocean waves of the same period generates standing ocean waves. This interaction generates a nonlinear pressure variation in the sea column that transmits into microseismic energy at a frequency of about 0.2 hertz through the seafloor and microbarometer energy above the ocean surface. This figure is from Kedar et al. 2008. They used the NOAA WaveWatch 3 program to generate the predicted standing wave intensity from directional wave spectra. They overlay surface wind vectors and show that surface winds are generally opposing in the area of high intensity, just off the coast of southern Greenland. You can see white surface vectors going north here, and they're going south down here. Several authors have also shown that microbarometers are routinely generated off the coast of southern Greenland. This figure shows polar histograms of microbarometers, microbarometer back azimuths, I should say, detected during a single day on 4 IMS arrays. They're all pointing towards the west to a single location. Color indicates the relative density of intersecting back azimuths. The black contour indicates the 95% confidence region for a single source model. One can also correlate the opposing surface winds to the location of the microbarometers. They're going north again. Actually, in this case, they're going south over here, and they're going north over here. It's very close to the area where these microbarometers appear to be generating. More fundamentally, infrasound, I should back up. One can correlate infrasound and seismology, rather, may be useful for validating NOAA WaveWatch 3 modeling results. Obviously, if the NOAA WaveWatch 3 model has predictions of directional spectra, if those directional spectra predict microbarometer microseismic generation, that can be observed with seismology or with infrasound. More fundamentally, infrasound connects many disciplines spanning the solid Earth, oceans, and atmosphere. So, USArray. The USArray transportable array comprises 400 stations at which there are co-located seismometers and infrasonic sensors. The station spacing is about 70 kilometers. The stations exist for about 2 years before they move east to a new location. They are currently moving into the eastern states and will be redeployed to Alaska in 2014. Because of the dense spatial sampling of the seismoacoustic wave fields, the USArray offers many unique opportunities to study processes involving infrasound and the solid Earth atmosphere boundary. We started off our infrasonic studies using the seismometers of the USArray. The seismometers can be excellent infrasound detectors. This is a seismoacoustic array in western Nevada run by Southern Methodist University. An infrasonic signal crosses the array at 330 meters per second and is clearly recorded by the microphones. However, the co-located seismometers at each site registers the signal as well, with approximately the same signal-to-noise ratio due to the acoustic to seismic coupling phenomenon. Zooming in even further to the worst and best case scenarios, it is clear that while the waveforms do not match precisely, there is a considerable amount of infrasonic information registered by the seismometers, which are here and here. Now I describe how we use single station sensors that detect infrasound to locate infrasonic sources. The method is called reverse time migration. There are many different names for this method. Energy recorded by the sensors is computationally propagated outward in all directions using an assumed group velocity. Where the energy interferes constructively is a potential source location. This slide shows 5 synthetic waveforms generated for propagation at 290 to 300 meters per second from the star in the map to the different stations. Those are the triangles. A grid of potential source points in X and Y is shown. A dashed, or I should say the dashed concentric circles expand outward in 200-kilometer increments from a trial source location. The corresponding record section for that trial point is shown on the right. Because the infrasound in the 1 to 5 hertz band is not phase coherent across adjacent stations, we calculate the envelope functions which are phase coherent. The energy in the envelopes does not linearly move out with range. This is quantified by summing the amplitudes along a trial linear group velocity of 300 meters per second. This summation yields a stack function S, which is a function of x, y, t, and your trial group velocity. The summation along this line yields the value right here at 0 source time. But we don't just sum along a single trial group velocity, we sum along several. Because the trial location is not correct, the energy does not align along any of these trial group velocities. However, if you move the trial location to the actual source location, the energy aligns fairly well, and the stack function amplitude increases greatly with a signal-to-noise ratio of 43 dB for the trial 290 meters per second group velocity. The source location, time, and optimum move-out velocity, or group velocity, corresponds with the location of the maximum value in your stack function S. We applied this technique to a day of USArray seismic data recorded in February 2008. We calculate a detector function that registers peaks in S as a function of time. A signal was detected at this time with a signal-to-noise ratio of about 27 dB. This is a bolide that exploded in northeastern Oregon. The signal source time here corresponds to the XY position here. Color in this map view indicates the relative signal-to-noise ratio of the delineation of source position. The reference points in time and space are used to generate a record section over here on the right. The coherence of energy along the optimum velocity of 290 meters per second is apparent in a wiggle density plot out to about 800 kilometers range. Our work on this event has come out in 3 papers that are available on our website. One of these papers shows the need for a new phase labeling nomenclature, which I mentioned earlier. The RTM solution shown in the last slide was compared to the solution obtained by using a few infrasonic arrays separated by thousands of kilometers. Regardless of the 4 different methods used, the 4 infrasonic array solutions had uncertainty ellipses that were considerably larger than that provided by the relatively dense USArray. Using a measure of ground truth provided by video observations, it's the circle here, the RTM solution appears also to be the most accurate. We applied this method to several years of seismic USArray data from 2004 through 2008. The 2004 through 2006 time period corresponds to a time when the USArray was not yet fully deployed. The detections during this time period were not well constrained, and we do not hold them in high regard. However, the 2007-8 time period yielded 901 different sources. An analyst reviewed and graded each solution. A bootstrap method was used to estimate the uncertainty ellipses for all 901 events. This is an example of an explosion of a rocket motor from a site called UTTR in northwest Utah. The event yielded a signal-to-noise ratio of 27 dB and can be observed out to a range of about 600 kilometers with a group velocity of 300 meters per second. The 901 events define the Western U.S. Infrasonics catalog, or WUSIC for short. This is a 2D histogram showing the relative spatial distribution of all WUSIC events. The sources cluster around several hotspots of infrasonic activity. These hotspots correlate with military training areas and ordnance disposal sites. They do not appear to correlate with mine blast locations. Of course, the western U.S. is clearly a noisy place. The accuracy of these results was judged by comparing the uncertainty ellipses to the known source locations for UTTR explosions. The red star is UTTR. The black dots are locations on the RTM grid. The 67% uncertainty ellipses are shown. The ellipses generally enclose the true source location. The elongation of the ellipses in the east-west plane is a product of poor source-receiver geometry due to the anisotropic ducting of the infrasound in one direction or the other. There is a remarkable similarity in the statistical distribution of WUSIC source times. The events that we observe usually occurred during the work week, both for 2007 and 2008. Sunday is the quietest day of the week because nobody wants to work on Sunday. The events also generally occurred during the work day, between 7 a.m. and 11 p.m. This might even be the lunch break between 12 and 1. The optimum group velocities for all the high-quality WUSIC events show a peak at 295 meters per second. However, if you expand this histogram in time, a sinusoidal variation in group velocities becomes apparent. This variation correlates well with the variation in surface temperatures recorded across the western U.S. states, as well as the variation in average stratospheric temperatures. This is possibly the first observational study that shows the predicted influence of seasonal temperature on infrasonic propagation velocity. As mentioned earlier, the WUSIC source location ellipses are typically elongated in the east-west orientation. Two events that occur in the winter and summer near southwestern Idaho are now analyzed in more detail. The signal-to-noise ratio is shown in color, with a cutoff threshold of 0 dB. The thick black lines are drawn to separate stations that did and did not detect a signal. The lower maps show the stations with signal-to-noise ratio in grayscale on top of ray tracing results, where the density of the ray reflection points is reflected in color. The predicted zones of illumination by the rays match the general areas where observations are clear, suggesting that the stratospheric wind directions in the G/S model are correct. Those wind directions are given by the black arrows. However, the fine details of the delineation of the shadow zones and zones of convergence are not predicted well. The explosions at UTTR are precisely known in X, Y, Z, and time. Furthermore, in addition to recordings made by the USArray, a dense Iris Pascal network of seismometers was deployed from nearby the site towards the northwest. This source was analyzed in several studies to test the accuracy of the G/S models. As you'll see in subsequent slides, the addition of wind perturbations due to gravity waves adds fine-scale structure to the G/S models that permits these enhanced models to explain a much greater percentage of the observations. This slide shows the acoustic to seismic coupled signals recorded by the USArray in black. In red are the infrasonic signals recorded by regional infrasonic arrays. Different arrival branches are observed in this record section. The onsets of these arrivals are predicted fairly well with the standard G/S model, that's in green. However, the range extent of these branches and the temporal duration of these signals are not predicted well by these rays. These are just the observations, now separated into their different arrival branches. Recall that US is the first stratospheric return, US2 the second, and so forth. Color is group velocity. These were picked by hand from the previous slide by inspecting carefully the record section. Now the ray tracing results for the standard G/S model are overlaid for these branches. Note that where there is overlap between the rays and the observations, the group velocities are predicted very well. However, the spatial distribution of the observations is not well predicted by the rays, until one includes the effects of gravity waves in the background G/S model. So let's show that again. This is before you add the perturbations. There's plenty of observations not predicted well. And then as soon as you add the perturbations, almost all of them are not predicted. There was no cherry picking of the gravity wave realization used. Subsequent random realizations generate the same spread of the rays. This is seen for other UTTR events as well. The remarkable success here suggests stochastic perturbations may be the missing link to explain many previously unexplained observations. And finally, this is the record section again, this time looking at the Iris Pascal data set, which is much denser. The G/S rays are in green, and the red are the rays from the G/S model that has the perturbations in it. The perturbed rays illuminate the complete range extent and temporal duration of these arrivals. Fundamentally, this suggests that the temporally dispersed energy in these waveforms is a product of multipathing rather than forward scattering. We are just starting to analyze pressure sensors across the USArray. These sensors began to be deployed in mid-2011. This is a record section for an acoustic to seismic coupled signal from the Gulf of Mexico or from the Southern Atlantic. Envelope functions of the 1 to 5 Hertz bandpass filtered vertical component data are shown at the top. Below is the 1 to 5 Hertz data for cases where only the signal noise ratios are above 15 dB. Note there are no signals seen past about 1,200 kilometers range on these seismic channels. However, when one analyzes the co-located microphone channels, the coherence is easily seen past 1,200 kilometers range. The microphones clearly are recording infrasound with much higher fidelity than the seismic sensors. This is an example of a loud source detected near New Orleans using the same RTM approach as used with the seismic TA data. This source actually occurred in June of 2011 and has a signal-to-noise ratio of 30 dB. It also propagated across the Gulf states at an optimum group velocity of 300 meters per second. Because we are analyzing microphones now, we can interpret the amplitudes without concern for acoustic to seismic coupling complexities. The spatial distribution of peak amplitude for this event is elliptical in shape. This geometry resembles that observed by Southern California seismic stations due to sonic booms off the coast. Note the highest amplitude occurred near the predicted source location, and the source location process does not use amplitudes in any way. The previous RTM method summed along trial linear group velocities consistent with stratospheric and tropospheric waveguides. A detector function identified the optimum group velocity. This technique does not account for variations in group velocity as a function of azimuth or range. We expect such variations and therefore seek to improve our method to handle these conditions better. For example, the previous synthetics shown here are generated using a model in which there is no azimuthal variation in group velocity. It leads to an optimum group velocity of 290 meters per second, as shown, with a signal noise ratio of 43 dB. However, if we impart a 7% variation in group velocity as a function of azimuth and recompute the synthetic waveforms, the old RTM method now yields two stacks with the same degraded signal noise ratio of 41 dB. A potential solution to this problem is to use a matched filter that has dimensions that are sufficiently broad in time to allow for variations in group velocity with range and azimuth. In such an approach, instead of summing along a linear group velocity line, we sum the dot products of the matched filter in black with the envelope functions. The result is a single, more stable stack function with a higher signal-to-noise ratio of about 45 dB. The trick to this approach is to find a suitable matched filter. We are defining a matched filter at this point by generating a probability distribution function of group velocities predicted with ray tracing. We discretize the Earth's surface, and for every source point, we shoot rays in all directions. We then bin the stratospheric and tropospheric waveguide rays that return to the surface across all source receiver azimuths. We combine results into 10-day bins and generate PBS for these bins. This is an example for winter and summer for a source point in eastern Nevada. We're currently tracing 180 million rays from the Rocky Mountains to Bermuda. In the end, the second version of the RTM approach will yield a stack function that is dependent on x, y, and t, but now also dependent on phase instead of group velocity. I'm now going to talk about long period studies using the pressure sensors. John Teitel and Frank Vernon are analyzing anomalies associated with significant weather events, such as gust fronts, which are pressure waves generated by downdrafts at the leading edge of thunderstorms. Here are 4 barometric pressure traces showing a sudden increase in pressure that varies or moves with time. This correlates to a passing gust front that's moving towards the southwest, shown here in Doppler radar. The pressure sensors obviously can be used to study and monitor storm development, while the co-located seismometers can be used to detect heavy rain and hail. John and Frank are also analyzing seismic and pressure observations from tornadoes. Here is an example of where a potential EF3 tornado passed within 1 kilometer of station Y46A. The time when the tornado passed the station is shown by a blue line here and constrained by Doppler radar. An odd precursory popping occurred on the pressure channels just before the sudden increase in infrasonic noise, probably due to the winds from the tornado. The horizontal components of the seismic channel show these very interesting perturbations as soon as the tornado gets close to the site. These observations are still in the early stages of interpretation. 30 TA stations will soon be retrofitted with a full meteorological package to do more in-depth observations of weather events. Catherine de Groot Hedlund is leading a study on the detection of gravity waves and gust fronts across the USArray. Here are different filtered passbands of the barometric pressure channel at a station with a signal at around time 117.2. That's the Julian date. A signal can be seen across multiple periods from 8 hours down to 10 minutes. The highest amplitudes are on the longest periods. To get a sense for the apparent wavelengths of these signals, Catherine interpolates the long period bands spatially across the TA. This is a time slice at 0300, which was when a string of tornadoes occurred in the south. Note the radially symmetric anomalies around the tornadoes. At more distant range, you can see a very coherent planar wavefront. The time slices are separated by 30 minutes. The planar wavefront during this time can be seen to be moving towards the north and northwest. We are interested in an automated detection approach that determines the direction and speed of propagation of these gravity waves. For this, Catherine divides up the TA stations, shown as black circles, into triads using the Delaney triangulation scheme. The centers of the triads are indicated with red diamonds. The result is a network of triads that can be used with standard array processing methods to determine the direction of arrival of these gravity waves. Catherine developed a multi-channel correlation method for this purpose. She divides the time series for each triad into frequency and time segments. For each frequency time window, the waveforms are cross-correlated. A set of criteria are used to determine detections. On this graph here, time again is on the x-axis, period is on the y here and here. Color in this case is azimuth, and color up here is phase velocity. Two signals are detected. The first is a large amplitude signal from the south-southeast. The second, smaller signal, comes from the south-southwest. This is the signal we saw earlier in the interpolation maps. And what I should have mentioned was this station right here at the lower right corner of this box is the station is the station at which these waveforms are recorded. And you'll see here shortly, this is now looking at the direction of arrival for that large signal. So a subsequent filter was applied to the results of that multi-correlation approach. It's a spatial filter that preserves only detections that are consistent between adjacent stations. So now we're looking at propagation directions at each station or each triad of the resulting detections for the 4 to 6 hour period as a function of time. Again, 0300, 0330. Note that the north-northwest propagation direction, as we saw, is now recovered with the method. The apparent velocities are 30 meters per second up here and about 60 meters per second down here. We are working on the best method for quantifying the productivity of gravity waves simultaneously seen by the USArray. In addition to the contributions to gravity wave studies that the USArray can provide, it can also be used to detect and monitor gravity waves, which is useful to commercial airliners, especially near airports. So to conclude, the last 15 years of infrasonic studies have been quite productive. 4D atmospheric velocity models have been developed. It's a game changer, and they work fairly well. Several ray and full wave field modeling codes also now exist for advecting media. The global IMS array network is performing well, recording many types of infrasound in the presence of significant winds. And finally, many hypotheses have been developed that can now be critically tested. The seismoacoustic USArray is well positioned to test some of these hypotheses, especially when combined with observations from regional arrays. For example, such studies have led to the discovery of new infrasonic sources in the western US, the delineation of infrasonic arrival branches in unprecedented spatial detail, the testing of thermospheric attenuation laws, something I didn't touch on during this presentation, the validation of using stochastic approaches to add fine-scale structure to standard atmospheric velocity models, and finally, the detection and tracking of gravity waves across large distances. The USArray can be used for other infrasonic studies, of course, as well, such as those involving ocean waves, severe weather events, volcanoes, earthquakes, aurora, and inversions for atmospheric structure. That's it. Thank you for your attention.
All right. Thanks very much, Chris. That was really interesting. There's a lot that's being done with this data set. Chris opened it up for questions. If anybody has any questions that they have for Chris now, I would just say type those into the chat window. Try to make them as specific as you can so we know which slide you're referring to, if it's about a particular slide or image. We did have one question from the middle of the talk, and it was just with respect to a reference. The question was from Peter Gerstoft. On slide 19, I think he was curious about where that slide came from.
It's hard. It's for some reason it's hard to hear you. Say that again.
Oh, Peter Gerstoff had a question about slide 19. I think he was just curious where it came from.
Slide 19. Okay, let me go back to that slide. Hold on.
Sure.
Something's going on with my setup here. Okay, so this slide is a result of processing infrasonic data on IMS arrays shown as purple squares. So I processed.
Hey, Chris, can you put the... I'm sorry to interrupt. Can you throw that back into presentation mode? For me, it shows just your first slide.
Oh, that's odd. Okay. Can you see it advancing now?
No, I can't.
You can't? You can't?
I cannot.
Can you see this?
No, I don't see any movement on your screen. Can anyone else out there see the slide that Chris is talking about? That's funny. I've never had anything seize up like that.
You can't see any of this.
Yeah, Michael Hedlund says, yeah, I'm getting reports nobody can see beyond wherever you just were. It still says the first slide.
Okay, hold on. Let me see. Yeah, I don't know what's going on. It looks normal to me. I can just answer the question maybe.
Okay.
Maybe he remembers what the slide looks like. But the slide, the background color represents the intersection density of projected back azimuths of microbarometers detected on IMS arrays. And the black contour indicates the 95% confidence region using the data recorded by those IMS arrays to locate a single source model of microbarometer radiation. And I was comparing that location with the surface wind vectors predicted by the NOAA WaveWatch 3 model, and where those vectors were opposing spatially is is also the general location of where that 95% confidence region was located. I'm
Okay.
not sure.
Sorry.
Did that answer the question?
I suspect it did. Yeah. Um, we have a question from Chad Trabant at the Iris DMS, and his question is: how many atmospheric models do you typically have to sweep through in order to get a decent RTM solution?
Using the first approach, where we use just linear models that have no azimuthal variation, typically it's about nine between 250 and about 340 meters per second.
Okay.
But
Uh,
what's very important with that approach is to make sure you're using envelope functions that are sufficiently broad. Otherwise, you get into issues with galaxy.
okay, great. Thank you. I have another question from questions from Noelle Barstow. She's curious: are there any attempts that you know of to quote unquote remove the infrasonic signal from long period horizontals co-located seismometers of the USArray?
I haven't tried that. Um, it's a difficult problem because of the coupling, and you don't want to remove the wrong thing. But so to answer the question simply, no.
Okay. And a question from Patrick Taylor. Do you see any sort of earthquake signals on infrasonic data? Maybe earthquake precursors?
Earthquake precursors, no. When earthquake radio waves pass infrasonic sensors, um, that generates a signal on the infrasonic sensor, either due to the shaking of the sensor itself or due to the shaking of the earth beneath the sensor that creates infrasound that's measured by the sensor. That's one type of signal that the infrasonic sensor will see generated by an earthquake. Another type is what I was showing with the Tohoku example, where in the epicentral area of an earthquake, the surface is shaking, and that generates sound that travels through the atmosphere to the sensor.
Okay, thanks very much. I have a comment from Michael Hedlund. He's saying Chris might comment on how a sparse seismic network could be and still be useful for RTM. 70 kilometers is great, but how sparse could the network be for this to work?
A detailed study hasn't been done to explore that problem, but scaling the results from the 2007-2008 study, which we did in the paper, we scaled these results in the paper and commented on this, shows that for very large events, you should actually be able to use stations separated with the type of station separation that the GSN has, but only for very large events.
Okay, great. I have a question from Chuck Estabrook. He wants to know: do you think that the quote unquote bag of rocks noise suppression is better than the rosette suppression system?
No, I think the rosettes are better. That's because it's very hard to beat spatial averaging for wind noise reduction, and we've done studies using bags of gravel and 55-gallon drums, or actually larger gallon drums, big drums of gravel, where the sensors were in the gravel, and they do have a significant wind noise reduction of 5 dB maybe in the 1 to 5 hertz range. But to get the 10 or 15 dB that really makes a big improvement, one needs to average right now over space. And that's why the IMS arrays use those wind filters.
Okay, great. Thank you. I had a general question. When you're locating these events, if you don't know what the source is, how often are you able to sort of identify what the source might have been? I guess my question is: how many sort of unknown sources are floating around out there?
That's a very good question. We don't claim to know the origin, uh, the actual mechanism behind these sources. They seem to be related to human activity. We can envision sonic booms being a very efficient generator of these sources, as well as explosions on the surface due to ordnance disposal or um, in bombing ranges where they're doing military exercises. We know from previous experience in Southern California, especially back in the earlier 20th century, that long guns um, that are tested off the coast during naval exercises also generates infrasound that travels far when the conditions are right in the atmosphere. So it's difficult to say what's generating the sources that we see in the USArray data. Um, some can be correlated with known locations, but I think a lot of what we're going to see is probably related to sonic booms happening just off the coast where aircraft can break the sound barrier without causing much nuisance in general to the general population.
Okay, great, thank you. Uh, unless there are any other questions, I think we'll thank everyone's muted, Chris, so they can't clap. But I thought it was a great webinar, and I really appreciate you taking the time out to share this work with us. I think it's fascinating. All right,
Well, thank
I'm getting lots of thank yous and clapping through the questions box. So yeah, I think everyone's very appreciative.
well, Andy, thank you for the opportunity. I really appreciate it.
Oh yeah, no, our pleasure. Thank you again. It's great to be able to share this research with the community. So anyway, thank you everybody for attending. And a recording of this will be available off of the IRIS webinar page, which is www.iris.edu/HQ/webinar within the next couple days. And I think if you have any other questions, comments, suggestions, concerns about the webinar process, or if you want to nominate someone to give one, please give us an email. We love feedback from our community. So, Chris, thanks again. Thank you, everybody, and have a great rest of your day.
Okay, thank you.